Yes.
All right. So my agenda is fairly standard, not much different from other guys. So let's get to the background. All right, so my name is Ivan. I'm a team lead of a deep learning team consisting of currently 6 people. We're developing deep learning solutions for a variety of industries, as well as using state-of-the-art approaches from a lot of deep learning areas, like computer vision, NLP, audio, you name it. Also, I've been participating on Kaggle for the past 5 years now. All of my gold medals are in computer vision, and most of them are in healthcare. So it was kind of like a perfect competition for me. Now, speaking about my solution, it's, in my opinion, fairly simple, but still. So the first important thing to note is that my solution is just a combination of 2D vanilla units with some post-processing to account for the fact that our data is essentially 3D, not 2D. Also, it's not mentioned here, but I trained this model on different crops from different planes based on the data provided by host. So essentially, we have 3 planes. We have XY, XZ, YZ. And during training, I sample random crops, usually of 512 by 512 pixels. And during inference, I simply use a sliding window approach with crops of the same size, but also with overlaps of half the size of crops. This is done in order to make sure that I fix the uncertainties on the boundaries of my crops accordingly. Then my unit models were powered by both convolution-based and transformer-based backbones. I tried a lot of things, but the best ones were EfficientNet, DPN, and MaxSuite, which is not really surprising because EfficientNet works like the best pretty much always, and the same thing goes for MaxSuite. Also, they both have fantastic implementations from Team, which is convenient to use. Now, speaking about important features of my solution, can you go back? I didn't finish. And one more. And one more. No.
Sorry. Is this good?
No, still one more to the back.
Okay.
And one more. Yeah, that's it. So speaking about the most important features of my solution, the first one was obviously pseudo annotations. So in this competition, we don't really have a lot of training data, and that's obviously an issue. So the way I decided to tackle this was like twofold. The first idea is, instead of creating pseudo annotations at once, I did it in several stages. So for example, I can train my models on kidney 1. Then I create pseudo annotations for kidney 2. I combine this data, train on it, and then create pseudo annotations for external kidneys that I found. Then I take all of that, train on it, and create pseudo annotations on external spleens that I found. And finally, I train on all of that, and that works very nicely. The second idea is that I don't use hard labels. In my experience, using hard labels is quite tricky. It can work, but it's tricky because your model obviously makes mistakes, and you treat those mistakes with a confidence of 1. You're like, I'm really sure this is the case, but it's a mistake. So it kind of breaks your training. And instead, I always try to utilize soft labels. In my experience, it works the best. So that's also what I did here. Then I had a composite loss. So I had a combination of losses. I had pretty much the classic stuff like computer or cross entropy, dice, and focal. Additionally, I modified the cross entropy a bit. I turned it essentially into a balanced cross entropy with more weights to boundaries of masks. So using some classic computer vision, I found boundaries of masks, I saved them, and during training, I just put more weight on top of these boundaries, since our objective metric cares more about boundaries, since we have, boundaries dice. Finally, I had 3D interpolation to account for different resolutions. So even in training, we had slightly different resolutions, but it was even more critical in terms of differences between public and private. So since these two scans are different in a 3D manner, I decided to use 3D interpolation, and it worked very nicely for me. So the whole code was written in Python with the usage of also fairly classic packages like PyTorch, segmentation models PyTorch, team, argumentations, stuff like that. And it takes roughly 1 week to train my whole solution on a single RTX A6000 Ada. Yeah. Now, feature selection engineering. This is essentially all about preprocessing. So in terms of preprocessing, I applied a lot of hard augmentations. I have shift, scale, rotate, random brightness, contrast. I have all the different flips, distortions, elastic transforms, and all of these things were used with fairly intense probabilities because, again, we don't really have a lot of data, so I decided to go all in. And also I used mean STD normalization simply because it worked. As I mentioned, to account for different resolutions, for a different resolution in private, I applied trilinear interpolation directly on 3D image, not just individual 2D slices. And again, it worked nicely. So getting a bit ahead of myself, actually applying interpolation on 2D slices also works. But since I managed to implement the 3D version of it, and it makes more sense theoretically, I just decided to go with that approach. Now, training methods. This is a simple semantic segmentation training, as I mentioned, with hard augmentations, composite loss, big batches, exponential moving average during training for stability, which is essentially just this sort of smoothing of weights, and stochastic weighted average after training for additional stability. Now, this last thing usually means several things. So in my case, it's very simple. I just pick different checkpoints during training, and I average weights for those checkpoints. Simple as that. Finally, my ensembles were created at the log gits level, as opposed to ensembling at probabilities level. Theoretically, this is questionable, simply because your models might learn to make predictions of different scales. So it might be the case if you have very different models, like, for example, convolution-based, maybe transformer-based. It could also be the case if you have very different losses. But in my experience in semantic segmentation, just ensembling on log-gits level pretty much always works the best, at least for strong models. Now, interesting findings. So what really set me aside from other teams, at least teams not in gold, was not overfitting to the leaderboard, at least to the public part of it. So I try to make sure that my solution is stable across different images and different confidence thresholds. What it means is you can take a full 3D scan, compute metrics on it, and then you can try to take different subsets of this scan, at least continuous subsets, and check the stability of your score. If it's stable, that's good. If it's not stable and you just got lucky, well, that's bad for you. And the same thing goes for confidence thresholds. So in this competition, it was quite interesting because for me, low thresholds worked fantastically well. But it should be noted that even at high thresholds, the metrics were fairly nice. So it was stable in terms of different images and confidence thresholds. So I was confident in my standing on the public. Also, this doesn't really change anything, just a cool finding. I found that knowledge that my models learn based on kidneys, it transfers quite nicely to spleens. That's why I decided to use it as a part of my final solution. However, that's not really the case for other organs like lungs, and especially not brains or hearts. So for lungs, it still predicts something and it makes sense to my eyes, but for brains and hearts, it's like complete bollocks. Now, simple model. So as I mentioned, I had a fairly big ensemble that took like, I think, 9 hours to inference on both public and private. And if I had to pick a single model, it would be the following. So first, I would use slices only across the XY axis, because those brought the most improvement. Then I would take the 2D unit with transformer backbones, simply because it works better than 2D unit with convolution backbones. I would still use composite loss because it's free. And I would use crops from different organs and different scans, not to overfit to a particular 3D image, which is a big concern if you don't have a lot of training data. So yeah, the most important model of my ensemble was 2D unit with a transformer backbone, and my ensemble scored something like 0.69 on private, and best single model scored 0.66 for a single model. I think those are correct because it's very difficult to sort out all the submissions, but I think that should be about right. Now, do you have any questions about my solution?